As physicists, we've enthusiastically expected this second for more than a century of all time. Starting around 1916, this occasion denotes a weighty accomplishment, offering a brief look into one of the universe's most fascinating and cryptic peculiarities: dark openings. These infinite Goliaths, known for their gigantic power, remain amazingly subtle. While they are enormous in terms of their gravitational impact, they are almost undetectable to us, making them considerably more puzzling. One such dark opening, possibly gauging between 2 to 4 times the mass of our Sun, may be the subject of this revelation. Over the past couple of decades, the exploration given to dark openings has changed our understanding, taking us from a position of outright obliviousness to one where we are beginning to get a private look at them. And now, things have taken a significantly more exciting turn, as physicist Kaku has uncovered that we have finally figured out how to look inside a dark opening. This discovery makes the way for an abundance of new data that could enlighten parts of science that we might have previously disregarded. Let us take a deep dive into the domain of dark openings and uncover what exists in them. While space is limitless and immense, the concept of dark openings raises innumerable questions. Before we dive into the particulars of Kaku's exceptional discoveries, it's fundamental to understand the key nature of dark openings. Most individuals have a basic understanding of what dark openings are, but huge gaps in our knowledge still remain. The theory of dark openings traces all the way back to 1916, when Albert Einstein published his general theory of relativity. This hypothesis predicted the presence of dark openings, but at that time, the idea was simply theoretical. It wasn't until around 50 years later, during the 1960s, that substantial proof for their reality began to surface. Researchers studying the heavenly body known as Cygnus noticed a strangely dazzling blue star emanating X-rays. This star, they found, was not fixed but rather was orbiting a massive dark object. Upon further investigation, it became clear that these X-rays were being drawn into this object, prompting the instituting of the term dark opening. This discovery was a fantastic turning point, as it confirmed that dark openings were not simply a result of Einstein's imagination. They were truly observable entities that existed in space. It became apparent that we needed to study them more thoroughly. Scientists from around the world began to focus their research on a specific dark opening in the Cygnus star system, designated Cygnus X1, which lies around 6,000 light-years away from Earth. This dark opening was multiple times more brilliant than the Sun and exhibited extreme density, with a gravitational force so intense that not even light could escape from it. This was the defining characteristic of a dark opening, the ability to trap light within its gravitational pull. The concept of a dark opening is both captivating and frightening. A dark opening is a region in space where gravity is so strong that nothing, not even light, can escape from it. Any object that ventures too close to a dark opening is sucked in. Once it crosses a critical boundary, it is lost forever, never to be seen again. This inherent danger is why it's so crucial to expand our understanding of dark openings. After the discovery of Cygnus X1, scientists embarked on a thorough search for other dark openings. Estimates now suggest that there may be more than 100 million dark openings scattered throughout the Milky Way galaxy. However, due to their nature, these astronomical giants are extremely difficult to detect, meaning we don't have an exact count. What is clear, though, is that there could be millions of dark openings within our galaxy, highlighting their significance in cosmic research. The primary focus surrounding dark openings revolves around their gravity. Their gravitational power is so immense that anything that gets too close is progressively compacted to an extreme degree until it becomes a singularity. To put it plainly, dark openings function as astronomical vacuum cleaners, pulling everything in with an insatiable force. One of the most disturbing aspects of dark opening research is that if someone were to fall into one, they would be stretched out into an elongated shape due to the tidal forces acting on them. This stretching would happen gradually, and the individual would die before reaching the final stage of this cycle. So, let's be clear, it's best to avoid falling into one, no matter what. Despite the closest dark opening being located nearly 500 light-years away, this still raises questions about the potential dangers they pose to us. In 2021, a remarkable achievement was accomplished when researchers successfully captured the first clear picture of a dark opening. This particular dark opening was located in the galaxy M87. The research team took several pictures over a few nights, and by stitching these images together, they created a comprehensive photo that revealed surprising details. It seems a dark opening is not just one massive void of nothingness, as many might think. In fact, a dark opening consists of 3 distinct layers. The first layer is called the event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be drawn into the dark opening. The second layer is known as the photon sphere, a region where light itself can be trapped in orbit around the dark opening. Any light entering this region becomes trapped by the dark opening's gravitational pull, unable to escape. The final layer is the singularity, where everything that falls into the dark opening is crushed down to an infinitely small point. This is where the laws of physics, as we know them, completely break down, and it's impossible to predict what might happen. What's even more fascinating and unsettling is that no 2 dark openings are exactly the same. While they all follow this 3-layer structure, the way they operate can differ dramatically from one to the next. Traditionally, researchers would rely on telescopes to observe celestial objects, but when it comes to dark openings, this method isn't feasible. Since dark openings are invisible, scientists can study them indirectly by observing the radiation they emit along with the surrounding gas and dust. Sending probes like Voyager to explore a dark opening is out of the question, as anything that crosses the event horizon would be pulled into the singularity, where it would be destroyed. Therefore, scientists must study these extraordinary objects through a 2-dimensional lens, despite their inherently 3-dimensional nature. One theory regarding the formation of dark openings is that they result from collapsing stars. When a star consumes its fuel, it can no longer generate the energy needed to counteract gravity, leading to an internal collapse that may eventually create a singularity. To further explore the nature of dark openings, NASA scientists turned their attention to the center of the M87 galaxy. Here, astronomers observed a massive whirlpool of superheated hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of this spinning gas should have caused it to fly apart, yet it remained intact. Scientists theorized that a titanic mass at the center of the galaxy, weighing as much as 2 to 3 billion times the mass of the Sun, was keeping it in check. This mass could only be explained by the presence of a dark regions of space-time, allowing for the possibility of interstellar travel or even time travel. However, the stability of such a wormhole remains a significant challenge. According to general relativity, wormholes require an exotic form of matter with negative energy density to keep them open. This exotic matter, sometimes referred to as negative mass or exotic particles, has never been observed in nature, making wormhole travel purely theoretical at this point. Despite these challenges, the study of dark openings and wormholes continues to captivate physicists and astronomers alike. Advances in quantum mechanics, string theory, and cosmology may one day provide new insights into these mysterious cosmic phenomena. Some researchers speculate that quantum entanglement, a fundamental concept in quantum mechanics, could play a role in stabilizing wormholes, potentially allowing for safe passage through them. Others believe that understanding the nature of black hole singularities could lead to groundbreaking discoveries about the fundamental structure of the universe. In recent years, space agencies like NASA and the European Space Agency, ESA, have been developing advanced telescopes and observatories to study black holes in greater detail. The Event Horizon Telescope, EHT, which captured the first-ever image of a black hole in M87, continues to provide valuable data, shedding light on the behavior of matter and energy near the event horizon. Additionally, upcoming space missions, such as the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves produced by merging black holes, offering further insights into their nature. Beyond scientific curiosity, understanding black holes could have profound implications for the future of space exploration. Some theories suggest that black holes could serve as energy sources, with their immense gravitational pull being harnessed for propulsion. Others propose that studying the physics of black holes could lead to the development of new technologies, such as advancements in quantum computing and space-time manipulation. As we continue to explore the universe, black holes remain one of the most enigmatic and awe-inspiring phenomena in existence. They challenge our understanding of physics, push the boundaries of scientific discovery, and spark the imagination of scientists and science fiction enthusiasts alike. Whether they hold the key to interstellar travel, new dimensions, or simply a deeper understanding of the cosmos, one thing is certain: our journey into the mysteries of black holes is far from over. Focuses in space-time, possibly in any event, connecting unique universes or various moments in time. Pundits, however, argue that the mongrel wormhole might be unstable or impossible to navigate due to extreme radiation and the forces at the quantum level. Some physicists point out that Einstein's equations, used to describe black holes and wormholes, do not account for the quantum forces that govern subatomic particles. To truly understand these phenomena, another theory that unifies quantum mechanics with general relativity is required. Such a theory, known as a theory of everything, could explain how the universe functions at every scale, from the smallest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for many years. One promising candidate is superstring theory, which suggests that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is seen as a symphony, with various particles corresponding to different vibrations of these strings. Superstring theory also provides potential explanations for black holes, wormholes, and other exotic phenomena by demonstrating how strings warp the fabric of space-time. Despite its promise, superstring theory remains highly speculative, as it requires extra dimensions of space-time that we cannot yet directly observe. These extra dimensions could be so minuscule that they are effectively invisible to us. Some theorists propose that these dimensions were more prominent at the beginning of the universe, during the Big Bang, and that they collapsed as the universe expanded and cooled. Superstring theory's potential to explain black holes, wormholes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of space-time, black holes, and the nature of the universe itself, there is no doubt that much more remains to be discovered. Perhaps we have only begun to scratch the surface in understanding black holes and their true nature. Michio Kaku's work in string theory and ideas surrounding quantum gravity have only started to offer potential answers. Even though we have gained a clearer picture of black holes through technological advancements, such as the Event Horizon Telescope and new methods of indirect observation, much remains beyond our grasp. The frontiers of theoretical physics, particularly concerning black holes and space-time, remain an incredibly active area of research where much speculation and exploration await. Despite their undeniable role in shaping the fabric of space-time, black holes have become central to discussions about the origins of the universe itself. As string theory suggests, collisions between universes could lead to the formation of new ones, and black holes might play a crucial role in this process. Such a theory could propose that our universe was born from a collision of two previously existing universes, or perhaps even suggest that we reside inside a black hole, a concept that would radically change our understanding of the cosmos. If this idea holds true, it could challenge everything we think we know about the Big Bang. We might begin to see black holes not merely as destructive forces, but as potentially creative ones, gateways to other realms or parallel universes. While the notion that black holes could serve as portals to other universes or even be key to understanding time travel is fascinating, this idea remains purely theoretical. The mechanics behind wormholes and the possibility of navigating through them remain a major mystery. Even if wormholes are stable enough to form, there is the question of whether the extreme radiation and forces near these structures would make them impassable. Some physicists speculate that if we could stabilize a wormhole, it could theoretically allow travel through time or between distant points in the universe. However, this remains a distant dream, at least with our current technology and understanding. Additionally, when we view black holes through the lens of quantum mechanics, we encounter even more intriguing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at observable scales, and the laws of physics seem to break down when we consider objects like black holes. This inconsistency between quantum mechanics and general relativity has been one of the most significant challenges in theoretical physics. Theories like superstring theory offer a potential framework for reconciling these differences by introducing extra dimensions and providing new insights into the nature of gravity. However, this theory has yet to be experimentally confirmed, and many of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to unify these two great pillars of physics, quantum mechanics and general relativity, into a single theory that can explain the full range of phenomena across all scales. Such a theory of everything would not only deepen our understanding of black holes and other exotic objects in the universe, but could also illuminate the very nature of space-time itself. The concept of extra dimensions, as predicted by string theory, might help explain the hidden forces that govern the universe. It suggests that what we perceive as a four-dimensional reality may actually be just a small slice of a much larger, more complex structure. Another major area of study is the role black holes play in the formation of galaxies and the larger structure of the universe. The discovery that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions about their impact on galaxy formation and behavior. It is speculated that these black holes may regulate the growth of galaxies, control the rate of star formation, and even play a role in the ultimate fate of the universe. The idea that black holes could have such a powerful influence on shaping the cosmos adds another layer of complexity to their already enigmatic nature. Additionally, the intense radiation emitted by black holes, known as Hawking radiation, named after the renowned physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of the information that falls into a black hole. For decades, scientists have debated whether information is lost forever when it crosses a black hole's event horizon, an idea known as the information paradox. Hawking's groundbreaking work suggested that black holes could emit radiation that slowly causes them to evaporate over time, potentially resolving the paradox. However, this remains an area of active research with no definitive answers yet. What is clear is that the study of black holes has not only provided us with remarkable insights into the nature of gravity, space-time, and the universe as a whole, but has also opened the door to new frontiers in physics. Black holes challenge our understanding of the laws of nature and continue to provide fertile ground for new theories and discoveries. As our observational tools improve, and as we delve deeper into quantum and relativistic realms, it is likely that we will uncover even more surprises, reshaping our perspective of the universe in the process.